For this elastography session, I, Tom Szabo, along with my equally invisible co-authors Kevin Parker and FAIUM, present Towards a Consensus on Rheological Models for Elastography in Soft Tissues. We compare shear wave data across decades of frequency and time taken by diverse methods and compare them to rheological, classical, and fractional derivative models in order to reach a consensus as to their suitability. Shear wave data are just patterns of points, but if we can find a rheological model that describes their behavior through a few parameters, then these parameters will allow us to compare data sets for various specimens, disease states, and environmental conditions. Because there is no agreement on which rheological model to use, the same data sets can give different shear wave moduli and therefore make comparison among different laboratories and clinics difficult. The goal of this talk is to provide the rationale and background needed to reach a consensus. Ultrasound shear wave elastography has turned out to be much more complicated than the original concept, in which the shear modulus could be determined from the speed of a shear wave front. While rheological models can account for some of the variations in bandwidth and frequency and position, additional factors such as the shape of the source may need to be accounted for and corrected for before the data can be entered into a rheological model. Ultrasound shear wave speed data plotted across 2 decades of frequency on a log-log plot indicates frequency power law behavior. A log-log plot makes a power law look like a straight line. Of viscoelasticity, the shear modulus is complex and has real imaginary parts. Here are 2 forms that are commonly used for data, the G or mu forms. Power law behavior is believed to be a consequence of tissue structure. For soft tissue, the multi-scale nature of tissue, extending from molecular chains to cellular walls, fluid channels, connective tissues, and large structures such as arterial walls, are likely combined to form the extended relaxation spectra. However, further research is needed to isolate and quantify the contributions in specific tissues. Here, the magnitude of shear modulus is plotted against frequency on a log-log plot, where straight lines indicate power law behavior. A diverse methodology has been used to gather the data, including rheology, transient ultrasound, elastography, and magnetic resonance elastography. What is amazing that this power law behavior is extended over 4 decades of frequency. Presently, mechanical methods like rheology and also magnetic resonance elastography, data can be obtained in complex form for modeling. This is not the case, however, in ultrasound for shear wave elastography, because an equivalent data set would require not only the shear wave speed to be measured, but also the absorption. While there is a model-less conversion possible between propagation parameters, CS and alpha, and the mechanical parameters, there may be additional corrections required. So overall, the process is more complicated for ultrasound shear wave elastography. Here we show some of the complications involved in rheology modeling. For rheology measurements, the modeling is more direct, but for magnetic resonance elastography, in which displacement is measured, or shear wave elastography, where amplitude and displacement are measured, there may be intermediate steps necessary before the model can be applied. The basic parts of a rheological model are an elastic modulus and a viscous modulus due to damping. The most common classical viscoelastic models from biomechanics are the Zener, Kelvin-Voigt, and Maxwell, the single relaxation models, and the multiple relaxation model shown to the right. Here are the three fractional derivative models, which are subsets of each other. The spring pot being a subset of the Kelvin-Voigt, which is in turn a subset of the Zener model. Note that the damper is now replaced by a diamond, which has another parameter alpha, which is the fractional derivative order. Here we see the chief difference between the fractional derivative models and the Kelvin-Voigt classical model. Fractional derivative models show power law behavior extended over several frequency decades, whereas the Kelvin-Voigt model diverges over a narrow frequency range. Here, the fractional derivative spring pot model is compared to a multiple relaxation model. Once again, we see that the multiple relaxation model is not able to describe power law behavior other than near the narrow range of data points. In this log-log plot, we see the magnitude of shear modulus of fresh bovine liver samples versus frequency follow a fractional derivative Kelvin-Voigt model very well over 4 decades of frequency. Stress relaxation measurements also for liver samples indicate a power law behavior in the time domain as shown in this log-log plot. This plot shows that the fractional Kelvin-Voigt and Zener models are quite capable of describing this power law behavior in the time domain, similar to the data shown earlier. We have compiled for the first time shear wave modulus data extending over 4 decades of frequency and time. These data indicate a power law behavior which is consistent with our understanding of multiscale tissue structures. The single relaxation classic models are unable to describe this basic biophysical behavior over this extended frequency range, and therefore we do not recommend them. The fractional derivative models, however, are able to describe this behavior both in the frequency and time domains, and we recommend the Kelvin-Voigt fractional derivative model as the most convenient of these for practical use. The use of these models for pathological tissues requires more study. Thank you. More information on these topics can be found in our journal article published in the Physics in Medicine and Biology, and in Sverholm's book, Waves with Power Law Attenuation.